Okay. So one last thing I didn't add before we went on the break about linked lists. Typically you have like minimum these functions. So you will be able to add a node to a linked list, remove a node, and then get. So get will return the reference to that node in that spot, which will also give you the value. But typically with the get, you send in a value and you are looking for that value, and then it returns the node itself. Any questions before we move on from these? Cool. Okay, so next thing we are going to talk about is hash tables. So linked lists and regular lists are pretty good ways of storing data. They're pretty versatile. One thing though is, what if you are trying to look things up more quickly? So if you have, let's say you have data, let's actually talk about key value pairs. So you have a key, you have a value, and you want a good and efficient way to store this information. What's the first thing that you can think of that would help store key value pairs?
Dictionaries.
Dictionaries. So dictionaries, if I'm not mistaken, are actually built off of hash tables. So there's this problem of having a key value pair and being able to retrieve that key value pair efficiently. So if you have, let's say, a list of these, so it's just key value, and let's say these are not numbers, these are all strings. So strings here, strings here. How can you actually look through this list? So let's say this is just an array. I know I did like the extra line here, but this is better. So if you want to look through this, you would probably have to look through every single one and try to find the data that you're looking for. But what if that's not possible? What if that's not possible, but what if your program needs a faster way of actually doing this? So hash tables actually use something called a hashing function. So this hashing function will essentially take the key, transform it, even if the key is non-numerical, so it's an actual string, it will transform it into some numerical value, and so this is now an integer. We're not actually like casting the key as an integer, but I'm just saying like the integer here, I'm just gonna say the key turns into an int, and this integer will then be kind of sized to our hash map, and each of these will become an index. So this key basically is transformed into an index, and that index will then tell you exactly which index you can access in this hash table, 3, 4, 5. So let's say if I put in apple and it gave me a numeric value, so let's say like 507. Let's actually not worry about the details of the hashing until like a few minutes from now. But let's say this one gave me an index that is 3. So every time I have a key that is called apple, I will insert that value that is attached to it into bucket number 3. So this is number 3. And here I have Apple that was transformed. So this is the value that was with Apple. And it gets put into here. Let's maybe see some code and try to visualize it a little bit more. But actually, before we do that, any questions about hash tables? We didn't really cover too much, but
I have one.
Yeah.
What if you have like oranges equals 3?
So that is, yes, so that would cause something called a collision. So instead of having this bucket in here, so this is an array, instead of having each value be a singular value, what do you think we can do here?
Make it into a list.
Yeah, definitely. So instead of this array item being just a singular value, we can make it a bigger list. I'm gonna draw this actually out here. So it extends. And this list now can hold multiple things, and we could probably hold both the key and the value that we were trying to hold on to. And then every time we have a collision, or we have something that ended up in the third bucket here, we can just append it to this list. Key and then value. So let's say this is Apple, this is orange. So that's typically how you handle collisions. Some people, so let's say with an array, you have to know, like you have to have a fixed amount of space that is saved up for your items. What can I do? What other data structure can I use instead of an array to only hold the amount of information that I need?
I would use another dictionary, so it just hashes it to a new object.
Or linked list.
A linked list would work. Yeah. So the hashing, you're already hashing it to here. You could actually do that. I think it might get a little more complicated if you have like a hash table within a hash table, but I believe I've seen that before. But instead of using a list here, you can actually just use a linked list. So that way, this array is just little references. And if they're empty, they're just null or none. But if we have the first item, then we can append a node called Apple with a value of something. So like you can hold on to both the key and the value. And then if you need to append something else, you can add it there. So you don't have to hold on to an entire list of space. So those are just a couple different options for handling collisions. But let's actually see how hash functions are implemented. Any other questions before?
Yeah, I had one more. What if it's Apple equals 3.5?
So that will have to be handled with the hash function. So the hash function, actually, does someone know what a hash function typically is or is used for?
It just makes a value another value by using an algorithm. Yeah, that's pretty much that's basically what it does. A hashing function will take some value as an input, and it will return a hash that is that input plus some stuff done to it, some calculations or whatever your algorithm needs, and then it returns another value. So typically hashes are used for like passwords, like password hashing. You'll hear of password hashing as like you input your password, and then what is outputted out of that function is something that is not recognizable. Like if you just have the hash, it is very, very difficult
it's nearly impossible to go back to your initial value unless you have like how this hash was created. So typically hashing is a one-way operation. It's fast to hash a value. So if you take Apple and you run calculations and it gives you a number that's like 107, there's no way to get from 107 to Apple that is very straightforward, unless you know exactly what you're looking for. So that's why hashes are pretty powerful. Hashing the same exact input. So if I input Apple into that function twice, it should give me the same exact output. It should never be random, because we are using this as our access point to we're using this hash function as indices. So if I want to insert Apple, then it should give me the same index as when I'm trying to look for Apple as well. So I can't put Apple twice and then get two different numbers. Then my data structure wouldn't really work. It wouldn't be able to find it. Okay, so I want a new keyboard. So this is going to be interesting. Oh my God, what is happening? Hold on. I did something. There we go. Please. Okay. I do this. Nope. Okay. Hopefully you guys can see the font. Is the font okay? Or does it need to be bumped up?
That's fine for me.
Zoom in. There we go. Yeah, I don't know where the control button is on this keyboard. Okay. Okay, so let's create a hash table. So I'm going to create a class. I'm going to create an initializer for this class. And inside of this initializer, I'm going to create an array of arrays. So I'm going to choose an arbitrary size for my array right now. So let's say self.table. So this is going to be my hash table. And this table is going to be a list. And this list I want to initialize as a bunch of lists as well. And I can choose the number that I want. So to do this in Python, I can do, I want to initialize a list for I in a range, a certain range. So for this hash table right now, I'm just going to choose 64. That's a decent sized hash table. And I'm not going to do too much right now. My table equals hash table. So now when I initialize it, if I print not self, it's my table, table. Oops. There we go. So if I run this. Okay, so here we see it's a list of, I'm not going to count them, but I'm going to assume that it's 64 lists that are empty. So that is what this line did. It just initialized a list of lists. Okay, so we want to create, let's define a hash function. So sometimes you'll see functions that are preceded with an underscore. That just means that it's an internal function that this method will use. It's not going to do anything special. It's just for organization purposes and just knowing like what these are. So this hash function is supposed to take a key and then return something else. I'm not really going to fill it in yet. Let's define a few other functions. So we're gonna be able to set something in a hash table, and then we're going to be able to get something from a hash table. So this one will take self, and then it will also take a key and a value. And I'm just going to pass. And I'm also going to make a function that will enable me to get a key, get a value from the hash table based on a key that I provided with. Okay, so let's say I want to insert something into the hash table. I just want to save a certain piece of information. I could always do my table dot set, let's say name, and then Alice. Okay, so this is my key and this is my value. So how will I know where to put my Alice value inside of this list? So the way to do that is to transform this key that I'm trying to insert into an index, and that way I can choose one of these arrays as my bucket to hold my information. So when I'm in my set function, first I will need to grab my index. So an index is going to be created by the hash function. So self.hash, and hash will take in a key. So I'm going to send it the key. And then when we want to actually insert the data into that function, we can just say, what is it called? Self dot, what was it, table at index equals, so let's say if I initialize everything to just a random number, sorry, equals value. So let's say we didn't initialize it to lists, we can just initialize it to values. So a bunch of zeros. Oops. List indices. Okay, I'm not returning the correct thing. So this is the insert itself, the set, it's not working. But let's say I just have an array. I don't want to worry about the collisions right now. I'm just gonna make it very simple. We hash our key, we use that key, that index of that hash to then access that index at the table and then set that value into there. So basically, whatever my index becomes, the value is going to be Alice at that index in my table. Okay, so my set should work. Now let's just implement our hash function. So let's say the hash is going to be just a number right now. We're going to initialize it to 0 just because we don't have anything, what is it called? Yeah, we're not starting off with any specific number. And let's build the simplest hashing function. So one way that is typically done, this is typically done, you will loop through every character in your key. You will then keep adding on to the hashing function, the hashing variable. And what you are appending is a numerical value that is representative of this character that is in the key. So there's a function in Python called ORD, O-R-D, that is going to return an integer based off of a Unicode character. So any letter or anything that is within a string, it will return a number. So this can take my key, not my key, sorry, my character. And we will append it. So let's actually see what this returns. So number value, that, and then we can just print the number value. And instead of having this here, I'm gonna append the number value. So basically we're, for each character, we are grabbing the numerical representation of that character, and then we're adding all the numbers up. And then we can print what our hash is. And let's see what this does. So just say final, just so we know the difference. Okay, so what I was trying to insert is name and Alice. So it took name, it went into this function to hash it, and then it started looping through. So N gave us 110, A gave us 97, M gave us 109, and E gave us 101. And all of these added up, which is what this is doing here, gave us 417 in this final hash variable. So what's something that you notice? So if we use this hash as it is, what is an issue that could come up?
If you have an anagram,
Sorry.
if you have an anagram, it would be the same hash, right?
Okay. Yes, that is an issue. So we'll handle collisions in a bit. But before that, so what size is my array?
64.
Yeah. And what is this index? 417.
417.
Way
So
too
would I
high.
be able, sorry?
I'm just saying it's way too high for your.
Exactly. So if this is not, yeah, so the index 417 is not going to exist in an array that is only size 64. So can someone guess what we could do to this hash to give us a number within, like, between 0 and 64?
You could use the modulus.
Yeah,
to get the remainder.
definitely. What would the modulus do here?
It would give you the remainder, so you would never go over 64.
Exactly. So basically, modulus is going to divide. So it's going to take the hash, it's going to divide, we're going to divide it by the length of our table. So self.table. Table. And what this is going to return, so if our, yeah, so the modulus basically just returns a remainder. It does a division, and whatever is left that couldn't fit nicely in that division, that is the remainder. That's what it's going to return. So if you're dividing 417 by 64, it's going to only go into 64 a certain number of times, and then whatever is left is going to be less than 64. So that means it will fit within our table, which is exactly what we want. Okay, so now if we return this hash modulus length of table, this should be an index that fits very nicely. So actually, let's print it out before I keep hitting the wrong key. Okay. And if I run it again, so now it took 417, and with this operation, it is now 33. And 33 is a valid index in an array that has that is of size 64. Okay, so now you see that the errors all went away. Let's check if our table has been modified. So I'm going to print the table again. Dot table. And I'm going to remove my print statements. Now if I run it, I see the initial list was all zeros, and then the second list, after I added Alice, it went to the 33rd or the 33rd index, and it inserted Alex there, or Alice. So if I do this for a few other things, so my table dot set the age 43. Can someone give me another key value pair?
Fruit, orange.
Perfect. Fruit, and then orange. Or orange. Okay, so now if I run, I see in my modified list, I have Alice here, I have orange over here, and then I have 34 over here. So the hashing function does a pretty good job at dispersing the information and not causing collisions. So if you make your if you make your hash table big enough, you shouldn't have any issues with collisions, but sometimes it does happen. You inevitably will end up with a place where, let's say we do this. I want to insert my table.set, let's say main and something. So this word has the same letters as this word. So if you're just adding the integer representations of this word and this word, they're both going to be the same number. So this should cause a collision. If we run this, we see instead of Alice, it's no longer Alice here, it says something. So this is where a collision could happen. What was one of the options that we talked about that we can implement?
Make it into a linked list.
Yeah, a linked list. What's the simpler version of that? So right now,
An array.
yeah, so right now in our table is just an array that has a bunch of zeros, right? Of a bunch of like regular values. So a way that we can handle collisions is we can make this array a list of lists. So each index is now a list. What would we have to change in this case? So if I run this, you see now when these things were added, it completely replaces the list. And we still see that something replaced Alice.
Yeah, you're gonna have to append it to that empty.
Exactly.
list.
So in my set function, I'm going to access that index, but instead of setting the value equal to it, I'm going to have to append that value to that list, because at that index, this is a list, it's an empty list. So if we do dot append, I can hold on to my value. And there we go. So this is my initial list, and then my modified list. At the 33rd index, it has both Alice and something. So we held on to that information. Questions here? Okay, so let's try to implement the get function. So when we're trying to retrieve the information, we send in a key, right? What are we supposed to do with that key to be able to access the information at that point?
You'll have to send in the key, turn it into the sum of its ASCII characters, use modulus, and then since you have a list that could potentially have multiple items in it, would you have, at first, as we're developing in Python, you'd have to search for it inside of the list that's at that location.
Okay, so yeah, let's do one step at a time. So you said we are going to grab the key, we're going to hash it and get the index. And then we are going to access the table at the index, so self.table at this index that we grabbed. And so let's just print this out right now and see what we get. Okay. I'm not calling a get yet. So let's say get age. I need to go back here. My table.get. Okay. So after we insert everything, we want to be able to get age. So when it gets in here, it's printing out the item. So we could probably just access first index, and that will give us the age that we're looking for. What if instead of age, I had put name? So let's say we're not accessing the first index because we don't know what index it is. So name is going to give me multiple values. And here I'm only holding on to the value of the thing. So I forgot who was talking earlier. Was it Jose or?
Yes, ma'am.
Yeah. So you were saying we grab the index and then we can find the value within the list. How are we going to get the value now?
If you don't have like a secondary hash, then probably just a simple if something in if value in list after saying self.table at index equal to some variable.
So basically if val in
Self,
yeah. Okay.
Yep, and then you'd return it, and that would also help you with error checking, because if not, you can return something else.
So what is an issue here? It's squigglied here. We don't have access to the value. Sorry?
I'm assuming you want it to be the key that you're looking for, right?
So this is something that's an issue with the way that we constructed our hash table. In the hash table itself, we are only holding on to values, but when we're looking for stuff, we're looking through the key, with the key. So in my get function, I only have access to my key, but inside my table, there are only values. So I can't really look for the value that I'm looking for. So if I wanted to look for name is not in my table. I have Alice. That is what I want to look for. But it's not the same. So how can I modify my my table in this way to enable me to search?
Or can you just make them key value pairs inside that list that's inside of your hash?
Yeah.
Instead
not
of
inside
just
the
null.
hash, but when I'm actually holding, like setting the data, when I'm holding on to it to save it, yeah, I would instead of just appending the value itself, I can append a key value pair.
Yeah.
Yeah, you're right. So if I do key value, I can make this a list as well, but a tuple it works here as well. So if I am appending key value, if I run this is going to cause an issue, but it's okay. It won't actually break until. How do I? Okay. So here now I have both the keys and the values held on. So in my get function, how should I search? So I have my index, right? It's going to call it bucket. Okay, so my bucket is just the array at that index. So how can I search through this now? What? Just iterating through. Does that work? Yeah. So for item in bucket, if I can reuse this. So value is going to be which one, the first one or the second one?
It'll be the second.
The second one, yeah. So if it was, well, yeah, actually we can't do the value because we
Well, you
don't
want to look for the key.
Yeah.
Yeah.
So if key, we can say just equals, and then we can grab item at 0. So if the key that we held on to is equal to the key that we're looking for, then what do? Get, I think the get function is just supposed to return the value.
Then you return the
Yeah,
item.
just return the value.
Yeah.
So we can return, well, we already have the key, like the person who's looking for it is already aware of what the key is. So I think a better thing to return is the value of that key that the person is looking for.
Yeah.
So we can return the item. Oops, I went too far down. I'm gonna erase my print statement. Okay. So now if I run, I'm not actually printing anything out. So okay, so this is still working, the get, the set. Awesome. So now when I call get with name, it returns Alice. If I look for main, which is the second one, the anagram, it will return something, which is what we sent in with it. And it should work for all of it. So because my hash function returns the same thing over and over, anytime that I call it, anytime that I try to get an index based off of this string, I'll get the same result. So I can actually access the memory the data that I stored in that specific location before. Questions?
It might sound a bit ridiculous, but can you circle back to why we're using this? Was it something about search speed? I forget why we even went down this.
It's for access speed. So now, so basically if we were looking for something with fruit, if we weren't using some sort of hashing, if we weren't transforming this into an index, we would have to loop through every single item in the array to look for, to compare the strings, basically. We're looking for wherever it says fruit. And this will allow you to, so that the number of accesses that you're doing here is you're accessing one index. So that's one operation. And then however, it depends on however many collisions you have, then you would just have to do as many operations in there to look through those collisions. So it's much faster than having to loop through an entire array and look for all the items. So you can have a function that gives you an index and more, so you don't usually have a lot of collisions if you're implementing your hash table correctly. So best case scenario, you are getting like, you're doing like 1 or 2 operations just to find your value, versus if you had everything in an array, you are looping through everything. And again, this is how dictionaries are implemented. So dictionaries are like, we use them all the time, and it's because you're able to just give it a key and it gives you the information immediately.
Yeah, that was going to be my next question. At a fundamental level, is it quicker or less resource intensive to just go to an array at an index?
Yeah,
Why
100%.
is going to a key at a dictionary? Why wouldn't you just have dictionaries inside of dictionaries and not do any of this?
No, so dictionaries are based off of hash tables. So we're understanding the underlying concept of the
gotcha.
hash table. Yeah.
Okay. Plus, I mean, I guess with the hash function, you could like encrypt, like you were talking about passwords or whatever.
Mhm. Yeah.
That makes sense. All right.
Is there a rule of thumb for like how big your data structure is projected to be as to where you would want to use the hash table? Like, because I mean, if you know you're just going to be working with very small arrays,
Mhm.
you maybe don't care so much about looping through it.
Yeah.
Is there like, is that a
I would
thought
have to
that
say,
happened?
we might see this more on Thursday when we're comparing like array sizes and how it affects like the program running. But I would say like tens of thousands of records or hundreds of thousands of records, even more. That it depends on, yeah, if you're just looping through, because it's linear, it's going to be like the more items you add, the more time it's going to take. So yeah, bigger number. I'm not sure of an exact number, but it just depends on what you're doing exactly. If you're only looping, then I guess like.
And does the complexity of the hash algorithm affect how fast this all happens?
Yeah, if your hash algorithm is not quick, like this one only only does like a few operations, like the loop inside, it's only looping like a couple times because of the length of the string. So you're not going to have a lot, even if it's like 20 characters in length or something, or 100, it's not that bad. But trying to think.
But we're also only summing up the values of each character. If you have like a, an encryption algorithm or something, wouldn't it take a lot more processing?
It depends on the encryption, yeah. Because some encryptions you're like multiplying and doing some certain operations on the numbers. Some of them you are like, you're not typically looping through. I don't think encryption algorithms take too long to encrypt. The encryption itself is pretty fast. It's trying to crack the encryption where you have to do a lot of loops and a lot of like calculations and stuff like that. But typically a hash function is going to be fast. That's kind of the need. The need here is for fast insert and lookup, basically. So I don't imagine a hash function that can that will take like a very long time, except if you have like triple nested for loops, then you're looping through a bunch of things. I don't know, you can make it more complex, but it shouldn't be that complex. You can make it complex without having to do a lot of strenuous calculations and operations. I don't know if that even answered your question. I'm sorry.
I think so. I'm mostly just idle curiosity as to what the trade-offs are between this and normal looping and where that handoff should be in my head. That's
With hash tables, I think you should start using hash tables once you notice that your code is not working as fast as you want it to be. Like once you have a big enough data set where you you're noticing the time it's taking, then you might want to optimize for a hash table. I don't think a lot of people tend to use like the bigger hash table. I'm not talking about like a Python dictionary, because we all use dictionaries and stuff like that to optimize our code. But yeah, if you're struggling with a lot of lookups, that's when you want to do some sort of hashing. Yeah.
Thanks.
Other questions?
Oh yeah, I had one. Couple months ago, I would try to look up a hash map, and a lot of the times they show me hash tables. Are they the same thing or very similar?
I believe they are the same. Let me see.
They're just slightly different. I looked up a table that was comparing the two. But honestly, I don't really think you really need to know the difference day to day.
Let me see. So my first Google said hash map allows one null key and multiple null values, where hash table doesn't allow any null key or value. Okay. I'm not sure. Yeah. Oh, I think I found the same thing that you're referencing, like the hash map versus the hash table. Here, I'll put the link in the chat. Oh, Mason, I just saw your question of, instead of looping, I'm assuming this is in our get function down here. Like instead of looping, can we get it by saying if bucket at 0 equals key, then return bucket at 1. So you would have to loop through these because each bucket has a few items if there is a collision. So the reason why we made these into lists is because when you're adding multiple things that end up at the same index, you're going to have the case where your what is it called? Yeah, where you have like multiple things that need to be inserted into that data structure. Or into that place. Sorry. Did that answer or did that help?
Yeah, that did. Thank you. I was just wondering if like you can check the length of the bucket too and do an if else just to try to optimize.
Yeah, well, we won't know how many items are in the bucket. That's the thing. Because what if there were 3 items and the thing that you're looking for is the third?
Well, at that point, I would do the for loops. But if the length of the bucket equals 1, I can then return bucket 1.
I see. I think at that point, the number of operations you're going to do in that loop is going to be the same as just accessing that same one, because the loop is just looping through the one item. So you don't really have to have the extra for loops for that. I mean, the extra if statements.
Well, the internal like built-in function to get the length of it has to iterate through that loop too, right?
No, actually, those ones are so the length function, if if I'm not mistaken, accesses the like there's an internal variable that's typically held on to,
tracks
like
it?
every time, yeah, it tracks the length, so that way you won't have to loop through it. Yeah. So that's a point of optimization. A lot of times you'll see that instead of the operations where you need to count things like size or length or something like that, built into the data structure or data type, whatever it is, you'll just see a variable that is holding on to a count, and every single time an item is appended, that count is increased. So when you want to find the length, you can just get the total or get the count. That easy return. Yeah. Other questions? Okay. Before we take another break, I'm just gonna see if there's a hash table one here. Let's see, I see it up here. Okay, don't know the difference. So we're just gonna go to one. So let's say we want to insert fruit. Oops. Why is my keyboard not working? Oh, it only takes numbers. Never mind. So 34. Let's say I want to insert this number. Ended up there again. Let's say we want to insert this. It ended up there. So this always depends on the hash function that the person is using. Sometimes you just take a number and you just modula, like do a mod on it to get the index. So yeah, when you want to find something, let's say 34. Oops. So yeah, it found the index and then it went through. And this is a representation of how you can do it in the linked list. We had it where this is our table, like this running list over here was our hash table. And then each one of these was an array that we created. Here they're using linked lists. So they're using little nodes to hold on to the information. Let me see what the other example was. So if I strings, oops. It does like a bunch of other operations. Interesting. So yeah, that's a more complex operation to find an index. So something. Yeah, it's probably going to take longer. Cool. Oh, I guess this is, yeah, buckets are apparently something very specialized. So I think they section off like parts of the array as this is one bucket, and then they try to find overflow and stuff like that. So there's a lot of different implementations, but the most simple one is what we saw today. Any questions on hash tables, hash maps? Okay. Let me